Hey guys, welcome back to Genius Learning. All right, so let's take a look at another Physics 1 problem, but now we have still 2D, but now it's a little more involved. All right, so we're gonna have to understand vectors and a couple other things. So let me read out the question. We have a dog running in an open field, has components of Vx equals 2.6 meters per second, Vy is negative 1.8 meters per second at time 1 equals 10 seconds. So 10 seconds has already passed, and now we're measuring the speed of the dog. In the X, he's traveling that fast, and the Y is traveling this fast. First piece of information. Then it says for the time interval from T1 to T2, where T2 is 20 seconds, the average acceleration of the dog has a magnitude of 0.45 and in the direction 31 degrees measured from the x-axis towards the y-axis. All right, so the coordinate system is like this. All right, so x towards the y. All right, so let's take that information and see what we need to do with it. First question is at T2, which is 20 seconds, what is the X and Y components of the dog's velocity? All right, so we measured it at T1, we know how fast he was going, and now at T2, we want to know how fast he's going. First of all, we have something to deal with. We got average acceleration of the dog is 45, and the direction is 31 degrees. Okay, so let's take care of that first, and we're gonna write out we're gonna write out in component form what acceleration looks like. So in component form, the little vector to denote that is ax I hat plus ay j hat. So the I and j is the same thing as y and x. Let me just look a little more fancy. So this should have a hat indicating the direction. But we can draw the same thing with a j here and an I here. So they're the same exact thing. So I and x, j and y. So sometimes if you're describing a couple different things, you might use generalized coordinates like that. So that's what I'm gonna stick with, just to kind of get you away from just using these. So this is what the acceleration looks like as a vector form. It has two directions. So you can't just say the acceleration is this. The acceleration in the x has to be something, and the acceleration in the y needs to be described. Okay, and the way we do that is gonna be, let's do a review real quick. So we got, this is, so we're gonna do, this is y hat, this is x hat, and we have the average acceleration, right? We know the magnitude, and also, so this vector right here is gonna be the acceleration, and that's 0.45 meters per second squared. All right, so it says that the magnitude is at 0.45. Magnitude just means the distance from the origin. So from here to here, it's 0.45, and that is described by the vector notation. Now we're gonna break it up into two parts. So we have this one, which is this. Now we need to break it up into two parts, because they also told us that the direction it was going was above the x towards the y at 31 degrees. So this angle in there is 31 degrees. All right, so we know from trig that we should have, or we could break this component into two. And so we're gonna draw a dotted line here this is a right triangle now. Okay, and let's see, for those that don't know, maybe I should do this. Okay, this is opposite, this is 90 degrees, theta. This is sine, it's opposite, and this is cosine down here. And so we have sine theta is equal to opposite over hypotenuse, and cosine theta is equal to adjacent over hypotenuse. All right, this should just be a review for you guys. So we're interested in this side. I want to label this side. That means we want this, right, on this graph here. Maybe I should have drawn it the same way. So I'll just do this. Cosine. Okay, so now this is the same as this. We want this side right here, so we're interested in sine, right? And so if I look here, right, and I want opposite over hypotenuse, because I'm interested in this section right here, I'm gonna do opposite, right? Let's just fill it out here. So sine is equal to opposite, which we don't know, over hypotenuse, which is this, we do know. So 0.45. I'm gonna leave out the units for now. So opposite is the area we're interested in, and hypotenuse is this piece right here, always across from the 90 degree. So now let's put the 45 to this side, and so then we have opposite is gonna equal 0.45 times sine, and we could put the angle in because we know it, of 31 degrees. Okay, so this is the opposite side, and you could see, oh, this is hypotenuse. What did I do here? Okay, sorry, this is hypotenuse, this is opposite, and this is adjacent. Wow, talk about review. Hypotenuse, opposite, adjacent. Okay, so I guess that was good for me too. So sine is opposite over hypotenuse, and so sine of this angle is opposite over hypotenuse. We don't know the opposite, that's what we want, and we know the hypotenuse, which is this line right here, which is 0.45. Okay, and this value here I already calculated. Let's see. Okay, so we got 0.23, and that's meters per second squared. All right, this is equal to acceleration in the y, because it's in this direction here. All right, and so now, so we got this piece here, and the arrow's pointing up, and now I want this piece here. So this is A in the X direction. So we're gonna need this bottom line here, which is gonna be our adjacent. So when we look at cosine, we're gonna see cosine is equal to adjacent, which is the side we want, so we're gonna just leave it, over hypotenuse, and hypotenuse we know. So again, we move that over, and we just solve for adjacent, which is the side that we're interested in. And we got 0.45 times cosine of 31 degrees. And so now we got the adjacent side. So adjacent, which is this bottom line here, calculated to 0.39 meters per second squared, because that's acceleration, and it's the AX. All right, so sorry for the confusion here. I mean, I think you should know this, but just a review. It's how to break up this component into AX and AY. So to get to this point here, I can take this, or I can take this route, boom, boom, which describes it a little more in detail. Okay, we broke this up. Now let's write it in. Okay, so let's write it in, and we're gonna put a vector is going to be so instead of putting the numbers first, right, AX is a cosine theta I hat plus a sine theta j hat. All right, and now we already know those numbers because we did it here, and so we're gonna put a cosine, which is this one here, right? The a is this 0.45, so when we put that over here, it becomes a cosine, which is a cosine, and that number was 0.39. I'm not gonna put the units for now. This is in the I hat direction, which is the x, and the other one is 0.23 in the j hat, which is y. Okay, so perfect. Okay, so now let's hold on to this. Okay, we have we've described it in now values, and let's look at the information that was given, right? We used the average acceleration, right, in order to break it up into components, right, and the angle. Now that we broke it up into components, let's hold this real quick, and let's move to the bottom. Let's see. Okay, so average acceleration, we can use this formula. Actually, I'm gonna write the formulas in this. So the formula we're gonna be using is the average acceleration, which is the change in velocity x over the change in time. I'm gonna do x first, and then I'm gonna do y down here. So I'm gonna do, this is gonna be vx1 minus vx over t2 minus t1. Okay, so don't get it confused here, right? Let me write it out here. So what I'm doing basically is this equation here, I'm gonna write it in a general form. So acceleration average is usually the change in velocity over the change in time, right? No x or y. And so you're gonna have velocity final minus velocity initial over time final minus time initial. Or you could put 2 and 1, right? So you could put velocity 2 minus velocity 1 and t2 minus t1. So the difference between this and now describing each vector is that I'm gonna have to do velocity x and then change in time, and then velocity y and then change in time. And so this x1 is the final, right? And vx is the initial. So don't get it confused. This is like where he was when we first clocked him at time 1, because time 1 is 10 seconds already. So the dog had enough time for 10 seconds to start running, and this is what we caught as the velocity. And so this x just means like the original x, maybe like at 0, and then x1 correlates to t1. So this is the final position for this time segment. Okay, so just to not get it confused, final minus initial, that's always the case. Our final is where we clocked them at the first time, and initially we were at some x value, maybe 0. Okay, so we end up clocking him again at a second time, and so that's why we label this one with 1, this one with nothing. All right, enough of that. So now we have this formula, right? So let me write the formula. I'm gonna do it like this to save some space. So we have here acceleration average equals Vx1 minus Vx, which is originally where he was at, and we have this now, right? Let's solve for this, which is the velocity where we first clocked him at 10 seconds. So I'm gonna pass this over, okay? So I should have acceleration average, right? We got T2 minus T1, I just pass that over. And then I'm gonna add this to the other side. So add Vx. All that's gonna equal Vx1. So I'm gonna have that. All right, so to save some space, I'm gonna use this formula, right, that I just calculated, or just derived from the formula, and then I'm gonna put in the values. So I'm gonna put Vx1, right, is gonna equal Vx, which was given to us, right? We have it here, 2.6. I'm not gonna put the units for now, but I know the units that I need to have at the end, because we have velocity, and velocity is meters per second, no matter what. So I'm just gonna not put the units throughout the problem, make it a little easier. Time 2 minus time 1, so we have plus Vx plus time 2 minus time 1, so this is 20 minus 20 seconds minus 10 seconds. And then the average acceleration was here. Okay, so this is another part that you might mistake. Since we're doing the velocity in the x, we need to get the average velocity that's in the x direction, which is this one. Don't get it confused with the original, because that's the total magnitude. Since we're describing the x direction right here, then we need to only use the x acceleration. All right, so that's a big spot to mess up in right there. So we're gonna use 0.39 because we're only looking for the x average acceleration, which maybe I should just write there. All right, and we got everything. So now we'll put that in the calculator, and we should get 6.5 meters per second. Okay, so we got velocity in the x direction, right? Once he was clocked, and now we're gonna do the y. So let's see. Okay. So now let's do again. We got average acceleration is gonna equal the change in velocity in the y over the change in time, which is equal to the velocity y1 minus velocity y over t2 minus t1. Okay, so again, we're gonna end up with the same formula once we solve it. So we have the same exact thing. We solve for the average acceleration. This one is in the y now. Okay, so we solve for Vy1. So we solve for this one here. So we're gonna get Vy1, right? It's gonna equal Vy. So hopefully you guys can see this here. So we're gonna have the same thing. So we're gonna have Vy1 is equal to Vy plus time 2 minus time 1, and acceleration in the y average. So V1y, we got Vy, which was the original, so negative 1.8 meters per second, plus the time, which is 20 minus 10, and then the acceleration in the y direction. So it's important that you understand that, because that's a big mistake that people make. So this one is describing the average, and it's made up of two different components, which is the AX and the AY. Since we're doing the segments separate, right, we want to know what the X and Y components are for the dog's velocity. We got to do them separate, and so we got to use separate accelerations. We can't just use this one to describe the X direction or that one to describe the Y direction. Okay, so we plug that in, and we got velocity y1 is equal to 0.52 meters per second. Meters per second, yeah. All right, so that's it. So this and this were for this. Okay, so we got the X and Y components for the dog's velocity, right, at t equals 20 seconds. All right, now let's do part B. And let's see what it says. Okay, so part B, let's see if we move this over a little bit. All right. So, okay, so part B, let's go here. So I'm just gonna whoosh, all the way up here. And can you still see? Yeah. So part B, we got, what are the magnitude and direction of the dog's velocity? So now we want to know the magnitude and direction of the dog's velocity. All right, and this is still at t equals 2, which is 20 seconds. Okay, so let's see what that means. All right, we have, let's see. Okay, so right now we have the initial velocity that the dog was coming in with at t equals 1, which is 10 seconds. Okay, then from t1 to t2, which was a difference of 10 seconds, 10 more seconds, you know, passed in this region. And now the dog is going at these velocities in these directions. So Vx, Vy are the original, and then Vx1 and Vy1 are now the new velocities that the dog is going in this time interval. Okay, now what it's asking you is, in that time interval, what are the magnitude and direction of the dog's velocity? Okay, so we know how much it's going in the X direction, right? And we know how much it's going in the Y direction. How much is it going in the magnitude, the overall? So let me draw a picture of that. So this is describing the following. Okay, we have this graph here, Y and X, right? This should actually be Vy and Vx. So their velocities in the Y, velocity in the X. What we found here is literally, let's see, we got Vx1, which is 6.5 meters per second. That's this area here. And if we just draw a dotted line this way with an arrow up, this one has an arrow sideways, we got Vy1 is equal to 0.52 meters per second. Okay, so these are the two things that we found. And what it's asking for is the magnitude, which is the one that cuts right directly to the point. So this is V with a vector symbol, and we want to know its magnitude. Right now we don't know it, right? And we want to know the direction. What is the angle that is made above the x-axis and the magnitude of this vector? How far is it and how fast? Okay, so that's where we're at now. We have this, now we want this. Okay, and so to do that, we use formula for magnitude. Okay, so I'm gonna do it again here so that way there's no confusion. Let's see. Okay, so I'm gonna do it here, and so usually magnitude, right? We have Vx squared plus Vy squared, and this will give us these two components together, squared and square rooted, will give us this middle vector, which is the magnitude. All right, so, but for this specific situation, we got to label things different. And so I'm going to label it, let's see, I'm going to put it here. So I'm going to put V1 is, and I'll put the vector symbol. I'll put this here as 1. And so we got the magnitude is going to be V, sorry, that's a V, all right, with this, Vx1 squared plus Vy1 squared, okay? And we already have those numbers, and make sure you guys can see that, okay. So we already have these numbers, right? And so it's just a matter of plugging them in. And so we got 6.5 squared plus 0.52 squared. And a couple calculations. Magnitude is 6.48 meters per second. Okay, we know that because it's velocity. Don't forget to write the units. So this is the magnitude. That's this one, that's this right here. Okay, the length of this vector and the speed is described by this. And now we can even find what angle it made. So we got another formula. Let's put a little checkbox in this. That's one thing we needed to find, which was the magnitude. And now we want the direction. So the direction, we need tangent theta equals y over x. Right? More specifically, we need tangent theta equal to Vy over Vx. Okay, so if we solve for theta, we're gonna get theta is equal to tangent inverse Vy over Vx. Okay, and we already have these two values, so plugging that in, we're gonna get theta is equal to tangent inverse of Vy, which is 0.52 over 6.5, and that's gonna give us a value, or theta, of 4.6 degrees. All right, so theta is equal to 4.6 degrees. All right, so we have the magnitude and we have the angle it's making. Now we can draw the appropriate graph that goes with this. So we have here Vy and we have here Vx. And so we know that this velocity vector is now 6.48 meters per second. And we know that the angle that it makes here is 4.6 degrees, which is probably a lot smaller than that, but I just wanted to write it in there. 4.6 degrees is probably like really, really small. So this graph directly represents the new direction or the new graph of the dog's speed at the different time interval, right? So we have the magnitude now, and we have the angle that he's going at, right? And we could describe it individually with the X and Y. All right, so last question is, what does it say here? Okay, so now let's do, where's the last? Okay, sketch the velocity vectors T1 and T2. So it's asking us to sketch the velocity vectors. Okay, T1 and T2. How do these two vectors differ? Okay, so how do they differ? Oof, that's ugly. Okay, whatever. So how do they differ? Let's take a look. All right, so we're gonna see what we're gonna need first. All right, so let's write out. Let's see, 35. Okay, so we're gonna do what we calculated first, right? So we already have this one, so that's fine. So let's do. We're gonna write out V vector 1, which is this right here. Okay, this right here, and we're gonna write it in vector form. Okay, and so we already did that once over here, but let's practice it again. In vector form, we have Vx in the I hat plus Vy in the j hat, right? This is X and Y. And the Vx we found to be 6.5. So we got V1 vector is gonna be 6.5 meters per second. And that's in the I hat direction, which is the X. And then plus we found, or we have here, Vy1 is 0.52 meters per second, and that's in the j hat direction, which is the Y direction. Okay, so this is written out in vector form, and we already know this looks like this. So for now, let's leave this alone, okay? And we'll worry about it when we need to draw the graph in a second. So now I'm gonna write out different colors here. We got now the next part. So we're gonna have, we're gonna use these, which were the original velocities that the dog came in with. So this right here is the change that happened, right? Where we're looking at a time interval of 10 to 20 seconds. This is like the velocity that's happening, the angle, you know, the direction. And now we're gonna go back to the original numbers, the ones at 10 seconds, and we're gonna find out how the vector, the magnitude is looking like, and the angle. Okay, so to do that, we're gonna express this as V without any numbers. We'll just put it as like the original. And we're gonna say that the Vx is gonna be 2.6 meters per second in the I hat. And then plus we have negative 1.8 meters per second in the j hat. So now that we have it in vector form, right, we know how to describe it up and down, but we need the angle. And so how we did the other angle, let me split this up. So this is for one graph. Now we're gonna do the other. So for the angle, again, we use tangent theta is gonna be equal to Vy over Vx. Okay, so inverse tangent of Vy over Vx. Vy is negative 1.8 meters per second, and Vx is 2.6 meters per second. So plugging this into the calculator, we're gonna get that the angle, the original angle, is 34.6 degrees. All right, so perfect. We have the vector, so we know where it's going and we know the angle. So now let's draw the final graph to tie it all together. Let me get a piece of paper. All right, let me just bring this over here. All right, so I'm gonna cover this part up. So for the final part, sketch the velocity vectors at T1 and T2. And so this part is different from, this is T1. Actually, this is T2, this is T1. Okay, so let's put the graph here, and we're gonna put velocity, right? This is Vy, Vx. Okay, so we know that this graph here corresponds to this interval in here. Okay, so we still have it as V1, right? And so this is gonna be the length of this vector, V1, and we know that's 6.48 meters per second at an angle of 4.6 degrees. And this is definitely not drawn to scale, so it should be a lot smaller, but just so everything could fit, and because I write pretty big. So now this is describing the V1, right? Which is what we got after the movement. So V1 corresponds to all this when we clock them again. Okay, it's a little confusing, the letters. I don't like how they label them like that, but it's, it's not too hard to understand. This part here is what was happening after we clocked them the first time. So T1 is all this stuff, right? Which is down here. And then through this interval here, this graph is what describes it. So this is the second thing. Now we're gonna go to the original thing. So now the original thing is at this degrees. Oh, and this is negative, sorry. Because you have negative 1.8 and over 2.6. So when the degrees is negative, you just go counter, you go clockwise. So you go down like this, 34 degrees, okay? And when it's positive, you go counterclockwise. So let's see, if we're gonna go down negative 34, let's just put it there, theta is equal to negative 34.6 degrees, all right? And the vector here, we're just gonna label with V, is equal to all of this. We can find the value of this just like we did with this one here, the magnitude. I guess, we can do it, but that's it. So we drew both of them. So let's just get the magnitude. Might as well finish it up. All right, so for magnitude, let's actually do it here. So for this part here, we got the magnitude, right, is gonna equal Vx squared plus Vy squared. And so that's gonna be, Vx is 2.6 meters per second squared, and the Y is negative 1.8 meters per second squared. So calculator, 2.6 squared equals plus 1.8 squared equals 10. Now we get the square root of that number. We got 3.16. All right, so let's make sure I did that right. Okay, so here we're gonna have, oh, and the units are meters per second. So if you can see it there. So this velocity magnitude is 3.16 meters per second. All right, let's just make sure, because I kind of suck at calculators. So 2.6 squared plus 1.8 squared, and square root of that, yeah, okay, so 3.16. All right, so now we completed C, which was sketch both velocity graphs, both velocity vectors. So this is one of them and this is the other. So let's see if we could interpret a little bit. So initially the dog was doing this right here, right? Going in this direction, right, with this magnitude of speed and at this angle. So we were like in a helicopter, we would see the dog running this way, boom, and at this speed and at that angle. And then, you know, and through a different time interval, 10 seconds to 20 seconds, right? He done something else and he's over here now. And so we can calculate the velocity in the Y, the velocity in the X, and find him at this coordinate over here now with an increased velocity of 6.4. So definitely running towards like some food or somebody he knows. Now it's 4.6 degrees above the horizontal. Okay, so that's the spot there. This was the spot before. All right, so that's it for part C. And I would encourage you guys, if you don't understand this part here with how to break up the vector into its components, that you practice that. And sorry for messing up a little, but trig is, you know, very old, but I see it's, you know, still messing people up. So breaking it up into components is important, right? Understanding, you know, reviewing your trig, and then understanding when you're given something. It says the average acceleration between this time interval is this, but this average, which should have a vector symbol over it, is two things being described. So in other words, this average acceleration is this line right here. And that only tells me from the origin to the actual spot. It doesn't tell me how fast I needed to go in the X direction for acceleration and how fast I needed to go in the Y direction for acceleration. So you need to be aware of that. That now when you see a letter and it doesn't have a subscript, red flag should go up saying, hey, you're not telling me the whole truth. And you need to find these two vectors, which is the truth, or like more, you know, direct route going through these different, you know, vectors. If you want to go through the X and then the Y, you need to know exactly how fast you need to go in order for you to make it there at the same time that you would make this trip here. So they're both the same thing. So this one is both of these, or both of these are this one, okay? Enough of that. The formulas, you gotta know how to use the general form without the little subscripts, and then plugging in the subscripts, making sure you put in the right accelerations here, which were found here doing the trig stuff. Okay, then we found magnitude and direction. Magnitude is the distance from the origin. All right, the direction is the angle. And just basically trying to piece together everything you're doing. And so you don't get lost in like, what am I finding this? What am I doing this part for, etc. All right, so I hope it was helpful. Comment below if you guys have any questions, and please subscribe to my channel. Thank you.